Welcome to Resolver. Today, we're going to show you how to export a project from a simulation tool like MELSOFT Gemini, tweak it using Resolver, and then bring it back into your simulation tool. Here, we've got a demo study of a spot welding application. Robots R1 and R2 have sequences called before, which include spot weld and home waypoints. It's important to know that R1 and R2 aren't sending set or wait signals, and their interfaces aren't connected. Let's run our programs in the main sequence, call the before sequence, and then hit run. As the simulation kicks off, each robot bumps into the workpiece because there aren't any VIA waypoints registered. Basically, the robots know where they're supposed to end up, but don't know how to get there without crashing. Plus, the robots start moving on their own, causing a crash in the middle. This happens because they aren't communicating with each other. Resolver is here to fix these problems. First, you gotta export your project using the Realtime Robotics connector. After you install the Realtime Robotics connector, make sure this icon is checked. Then, on the Export tab, pick the sequences for each robot you want to optimize. For us, we're going to pick the before sequence for both Robot 1 and Robot 2. Click the Export button. A warning will pop up, letting you know that self-collisions aren't set in your application. Always make sure to set the right collision rules based on your application. Let's go ahead by clicking OK. Depending on how big your project is, this might take a bit. When the export's done, you'll see a success message on the output panel. Then, head back to the Realtime Robotics connector and go to the Resolver tab. Here, we've got two operations, one for each robot. For the first robot sequence, we'll start setting up the Resolver to optimize. First, set the target offsets for the approach in the X, Y, and Z axis, or set the tool approach degrees. Do the same for the departure offset for each task. Next, set the allocation. This lets you assign Robot 1's targets to Robot 2 and vice versa. You can also tweak the target order. For example, in Robot 1's sequence, after the home position, the order is point 2, then point 3, followed by point 4. If going to point 4 after the home position cuts down the cycle time, Resolver will create the path with home followed by point 4. Just click Optimize Target Order to do this. You can set the interpolation type from joint to all targets or linear to all targets. You can also specify the motion type for each specific target. Under Configuration Settings, you can optimize the robot's setup or just the rotation in the desired axis. For example, optimize to RZ. Now, apply the same settings or preferred settings to the other sequence too. Once the sequences are optimized to your liking, you can decide how to end the optimization. As you can see here, there's a checkbox to enable smoothing. If you want values to be smoothed between targets, you can turn this on. Next, there's the condition. Under the convergence threshold improvement threshold, it's set to 1 millisecond and the time threshold is set to 30 minutes. This means if the Resolver can't cut down the cycle time by even 1 millisecond after 30 minutes, the optimizer will automatically stop. Alternatively, you can set the optimization to run for a set time, like 4 hours. Once you're happy with your settings, click Start. This takes you to a new page. Now, the Resolver is connecting to the cloud server and getting the CPUs, GPUs, and resources it needs. During the loading Resolver engine project data phase, the project's error and settings are checked. Depending on the size of the project, this might take a while. For this demo, we've sped up the process. Once the optimization starts, you'll see the reachability table on the right side. This table shows that all targets assigned to Robot 1 are reachable and collision-free. The same goes for Robot 2. However, the targets assigned to Robot 2 aren't reachable by Robot 1, as shown by the red marks. You can also see the estimated cycle time here. In a short time, as you can see, optimization can give great results. Let's check out the result preview in a 3D video. Once applied, you can see the active optimization of robot movements without needing to download the results. When you're satisfied, click on Download Results. This will prompt you to choose the interlock types. In our case, we have sequence and spatial interlocks. Let's go with sequence interlocks. After selecting, click on Import. The optimized path is successfully imported. Now you can exit the connector interface. As you can see, a new sequence named RTR Opti is added for each robot. For the target, we have via points and interlock statements, also known as sync statements. Let's run our initial program again. As you can see, there are collisions between the tools and robots, and also between the tools and the workpiece. Now, let's swap a statement with the final optimized statements for each robot. Now let's play. As you can see, our robots are moving without any crashes and with an optimized cycle time. Thanks a lot. That's it for our session.